Okay, Mark, you should be off mute now.
Okay, can I control this from my computer?
Let me make you a presenter.
I just feel a little more in control that way.
All right. You're good to go, Mark. Thanks. Have a great webinar.
Good evening. This is my fourth webinar in a series of 5 that Kush has described. The subject matter is the ASQ Automotive Division's approach to measurement systems analysis based on the 4th edition manual. And like the other seminars, the intent of this is not to take this 2-day course and to condense it down into a 1-hour session, because that'd be kind of silly, but instead to highlight how we're approaching MSA in the 2-day course, and also share with you, hopefully, some nuggets, some takeaways that you will find of value. So that's kind of my plan for this evening. My agenda in the 2-day course is we cover 5 basic chapters, and they're outlined here. We start with a review of quality statistics, because statistical control of a measurement process is essential to having valid measurements that we can trust. Measurement systems analysis, if you happen to attend the session that I did on the production part approval process, the purpose of measurement systems analysis is to allow us to trust our gauges. That's what this is all about. So I'm going to go through a quick review of some of the things that are in the course, and then on to fundamentals, fundamental concepts, preparing for MSA studies, the mathematics of MSA studies. I won't go too deeply into the mathematics, and then how do you evaluate the MSA studies? And by then, my hour will be up and we'll move on to questions. The course goals. I've identified 3 basic course goals. The first is that we gain a fundamental understanding of the language so we can hold meaningful conversations about measurement systems analysis. The second is that we use MSA studies to determine where the measurement processes that we have really need to be improved for us to accurately assess our special characteristics. And third, to achieve robust, capable measurement processes for those special characteristics. So, starting with quality statistics review, I start with Dr. Deming's definition of operational definitions. This is actually a quote out of the Crisis. He said, without an operational definition, investigations of a problem costly, ineffective, almost certain to lead to endless bickering and controversy. He went on to specify that an operational definition really holds 3 components. The first of which is that we all have a common test, so that from customer to supplier, from supplier to sub-supplier, we're all measuring things the same way. We also have the same criteria so that we can make judgments based on that criteria. What I'm showing in this slide is a feature control frame. And I show this feature control frame because it's an excellent example of an operational definition. We said in the last slide that there were 3 components. The first is we have to specify the test. Well, this happens to be a test for position, which is shown in the first compartment of the feature control frame. The second compartment of the feature control frame is showing us the tolerance zone. So it's a cylindrical tolerance zone that must contain the axis, and the diameter of that cylinder is 0.4 of a millimeter if we're at maximum material condition size, and we're related to datum A first, then datum B as a maximum material boundary modifier, and then datum C, in that order. So the structure for a feature control frame is the first compartment specifies a geometric characteristic. The second compartment is going to tell us the tolerance zone. The third compartment, if it exists, will define what feature is going to create the primary datum. The fourth compartment specifies the secondary datum, and the fifth compartment specifies the third datum. What this allows us to do is through the operational definition, the test, the specification relative to the datum scheme, is to allow us to make decisions. Is it conforming or is it not? Now, for most features, we have to locate things back to a datum scheme. And the way that we locate things on the perfect part is by specifying basic dimensions. They give us the theoretical exact size or the theoretical exact location of features on the part that we're looking to manufacture. Then we set the part into a datum reference frame on the primary datum surface first, then on the secondary datum surface, then on the third datum surface. So we make contact in the order that's specified in that feature control frame. The 2009 standard on geometric dimensioning and tolerancing, ASME Y14.5, 2009, has added some wonderful words that didn't exist in the 94 standard. They tell us that manufacturing parts have irregularities on them. Well, we know that. There's going to be high points on surfaces of part that are going to make contact. If you were to set it on a surface plate, it's going to make contact on those high points first. Well, in the real world, what we use are datum feature simulators, things of gauge quality like surface plates, angle plates, tables of machine tools, vices, all sorts of different datum feature simulators in order to establish our datums so that we can measure things from those datums. Now, the MSA guideline only gives about a half page to the importance of these datum features and the datum feature simulators, and it's buried about halfway in the middle of that document, the MSA 4th edition. But what I find in industry is that when people have dimensional problems, it's frequently, how frequently? Maybe 80% of the time, tied to a poor datum scheme. Either the designer has specified the wrong datums for the way that the part functions, or there's been no specifications of the datums, and a quality technician or an inspector or a process engineer is left to guess at how the part is intended to interact with its mating parts. So if we take a look at this example, it's a simple example. It's a plate, about 12 millimeters thick, just a spacer, 4 holes on it. There's a corner that's cut away for some clearance purpose, perhaps. The back surface is datum feature A, the bottom surface is datum feature B, and the left-hand side is datum feature C. And we've identified that we're going to locate this part when we go to check that 0.7 of a millimeter cylindrical tolerance zone for position that must contain the axis by setting the part on datum feature A first, then datum feature B, then datum feature C. So this is the same datum scheme, and here I have a datum reference frame. It's a plastic construction with 3 mutually perpendicular planes. And right now this part, which happens to be in wood, I don't imagine many of you make wood parts, but we paid extra to get these made out of square to drive some important points home. Well, here we're making contact with at least 3 points on that bottom surface on datum feature A to datum A, which represents, say, a surface plate. Then we move this part down until it makes at least 2 points of contact onto the secondary datum, and then we shift over to datum feature C to the first point of contact. I don't know how well you can see from this photograph, but it's out of square. Up at the top of this piece, there's a little gap there. Can you imagine checking the XY coordinates of the location of this hole compared to A, then B, then C? Now consider what would happen if we checked at A, then C, then B. And that's a legitimate datum scheme. We could do that. Well, then we'd have to make contact with datum simulator A first, then, because it's called out second, datum feature C second. And can you see this gap down here? The location of this hole just changed. That's a problem that we have if we don't have datum schemes to measure from, datum schemes that are specified on the part. So that's all I have to say about datum schemes in this course. Here's another concept, and it is fundamental. It comes from Donald Wheeler, and he certainly influenced me. He wrote a book years ago with Richard Lyday called Evaluating the Measurement Process. It's now in the 3rd edition, and he says no 2 parts are alike. But even if they were, we'd still get different values when we measured them. That's a concept of variation. There's variation in all things. So we can take some measurements, and some more measurements, and some more, and we can identify, if the process is stable, a natural variation inherent in the process. And I talked about that to some length at the SPC webinar, so you might want to go back there if you happen to miss that one. Well, a measurement process that is working as it should provide the natural variation inherent in that measurement process as being stable. So we can look at the way in which people interact with their gauges, the environment, the equipment, the material, the methods, how they load the gauge, and the people themselves, and those causes have a resulting amount of variation in the measurement process. That's largely what MSA studies are about. And we want to know when changes in behavior happen and we can no longer trust our gauges. That's what we want to know. And to do that, we apply statistical process control. We want to understand the behavior of the measurement process. The goal of that understanding is so we can make a prediction of how that's going to give, how it's going to perform in the future, so we can take appropriate action. I attended a session by Dr. Deming back in 1990, and he raised these 3 bullet points. I see it as a philosophy of actionable data, and I think if we're going to do measurement systems analysis, they ought to be for some purpose. So we raised these 3 points. No inspection without recording. How often do we inspect things and don't write anything down? We're just curious, or our customer is just curious. The second point, no recording without analysis. And the third, and in my view, most important, is no analysis without action. Knowing how to act requires that we plan to collect actionable data. So some processes are predictable, they're stable over time, and other processes aren't. We talked about this at some length in the course on SPC. And we have a control chart that'll show us stability or instability when that exists. Now, I used this drawing in that SPC webinar. Here we have a shaft, and there's a keyway that's cut into the shaft. And a reasonably tight tolerance, these are in metric, for the position and also for the size of that keyway, related to the axis generated by the surface extremities from datum A, datum feature A. In this example, we're going to look again at the width of the keyway in this view. Well, if we were to take typical Gage R&R data and plot it on an X bar and R chart, this is what we would hope to see on the ranges chart. Here we have 4/1000 of a millimeter, or 4 micron, as our average. And some of the points are above and some of the points are below, and it seems to be reasonably average. There's no surprises. There's no unusual trends that I can see in this data anyway. Well, when we look at a measurement process, we expect to see the range chart in control. But we also expect to see that the range of those measurements are very tight compared with the manufacturer of the part, and the tolerances on the width of that keyway were from 10 millimeters to 10.03 millimeters. Those are our tolerances. And you can see that we generate X double bar, which happens to fall right on the mean, conveniently enough, on the equal bilateral tolerance. And we have these relatively tight control limits that run from about 10.011 to 10.019. Now, if we do an X bar chart with the data that we collect from a Gage R&R study, in a Gage R&R study, we want to take parts. Some of the parts, we want them to be pretty close to the center or target value. And other measurements, we want to be close to the tolerance limits because we want to know if the measurement process can discriminate between those parts. So if we were to take the first of 3 operators and take the averages of those 3 measurements on each of those 10 parts collected randomly, this is what the pattern might look like. A lot of people aren't used to seeing this. By the way, the source material for this was from Don Wheeler and Richard Lyde's Evaluating the Measurement Process. Wonderful, wonderful book. But what we see here, in this case, is we have 8 of the 10 points that lie outside of the control limits. And if you're not used to seeing X bar and R charts applied to measurement systems analysis studies, this is exactly what we should be seeing. My assumption is that the slot of part number 8 is quite a bit larger than the slot of part number 3. That these have a reflection to the actual size of the slot of that part. So if we were to take the averages on those 3 samples of 10 parts from our second inspector, Inspector B, and we were to measure those, what would you expect to see? You'd expect to see a near repeat of that same pattern. Now, part 1 has gone up a little bit. Part 2 has gone down a little bit. There's a little bit of variation, but the same basic pattern is there. And what would you expect to see from operator or inspector number 3? Well, you'd likely see the same pattern again. This is what we ought to see. The X-bar chart applied to Gage R&R data examines the ability of the gauge to discriminate between different part sizes, different dimensional concerns. This doesn't tell us about statistical control. The range chart, on the other hand, does tell us about statistical process control. And if you've had the opportunity to do a Gage R&R study, they will have you do a calculation without necessarily plotting the data to calculate a threshold value. In this particular case, it came out to 0.0103, so I averaged it to 10 micron. The process appears to be stable. It's trustworthy. We can trust our measurements from our Gage R&R study. You'll see an example later on where there's a deficiency in the trustworthiness, but that's toward the end of the presentation. So let's move forward. I was in the room when Dr. Emil Jaby made this statement. Time frame would have been about 1991, 92. The presenter, this was for the Ann Arbor section of ASQ, and the presenter was Vic Lowe, who was a chief statistician at the time for Ford Motor Company. He was among the original group of authors of the first edition, we're now on the 4th edition, of the MSA manual. And he came out to our section, he was a member of our section, and came out to our section and did a Saturday session. Well, Dr. Jaby was this wonderful character. He, old, maybe 82 at that point in time, and white hair, tall, lean, would not tolerate things that weren't correct about statistics. And somebody said something in the room, and I forget what the actual thing was, but here I was, a young quality engineer at the time, and he said, if you are responsible for a measurement process, and I was, a whole bunch of them, and you're not measuring that process on a control chart, and I wasn't, not any of them, then you are not doing your job. And that statement just stabbed right through my heart. I knew he was right, and I knew I was wrong, and it changed some behavior. So the purpose of control charts is to make the right decision, to take action when action is required, and to avoid taking action, to avoid tampering with a process when we ought not tamper. So, now let's introduce some terms. Measurement systems analysis, and we'll start with this target analogy. We think of the ability, the goal is probably to hit the bullseye. That'd be my guess for just looking at the target. Well, if we have a plot that's really closely gathered, we say that that's pretty accurate. And it's precise. The precision deals with the tightness of the grouping. The accuracy deals with the average being at the bullseye. Well, this has its average at the bullseye, but it's not very precise. Here, we have a tight grouping, so it's precise, but it's off a little bit. We need to adjust our sight. And here, this is like the dartboard I had when I was a kid, and I got in trouble because I left a few holes in the wall. That just kind of happened. The next question deals with resolution. Ideally, we have 10 increments in our measurement device between the specification limits. The MSA guideline says we need 5 distinct categories as a minimum. There are some places where I would argue that with 4 increments, we could establish a procedure for pre-control with functional gauges, but that goes a little bit deeper than I have time for today. They say if we have less than that, it's certainly inadequate. Now, accuracy and precision. Those terms are neither accurate nor precise enough for our use when we're talking about measurement systems analysis. So we introduce 5 terms. They're bias, linearity, stability, repeatability, and reproducibility. When we look, this is actually a gauge block that we built to implement our calibration system, because the people in our company own their own measurement tools. They own their own micrometers and such, and they didn't want anybody else touching their micrometers. So you have to make quality work in the culture that you live in, so that's what we did. We made these blocks, and this might be something less than an inch, something around 3/4 of an inch, around a half inch, around a 1/4 inch for a 0 to 1 inch micrometer. And I don't care what size they are. What I care about is that the bottom surface is very flat. These surfaces are very parallel to that very flat surface, and I know what size they are. Well, can I ever know what size they are? Probably not. We don't know what the true value is, but we can get a certified value. It's a concept of measurement uncertainty. When we compare the size of these to a gauge block, how much measurement error is there? What's the tolerance limits to that measurement error? How well can we trust the measurement of these sizes? Well, for our purposes, we can trust them to 1/10 of a 1,000th of an inch with the methods that we put in place to make and measure them. Well, if we bring this block to a machinist and we ask them to measure these 4 things, we know the size, the certified size of each of these steps, and one step might be a little bit larger, and the next step might be quite a bit larger. We're interested in the average variation of these 4 steps in this particular case. It's the difference between the assumed true value and the measured value that is our bias. That's what we mean by bias. Linearity. If we look at a measurement device, in fact, we came across one micrometer in a shop. It happened to be a Craftsman micrometer. The spindle on it, the threaded part that actually causes the measurement to occur, was non-hardened. And the individual was responsible for making things about 3/4 of an inch. He ran a lathe, that's what he did, and he measured them, and he measured them, and he measured them for years. And what we found was that on that particular micrometer, because it wasn't made with a hardened spindle, it wore in that particular area. So that micrometer would measure pretty accurately if you were measuring something around a 1/4 inch or 1/2 inch, or even a full inch, but around 3/4 of an inch where that wear took place, he had more than 1,000th of an inch of error. Well, that's a problem. We got that micrometer out. That is a case of linearity error, where we have a small amount of bias in one area and a larger amount of bias elsewhere. If you ask your CMM operator to measure something very precisely, my guess is that they'd be able to know where their machine is going to measure more accurately than other areas, and they will find the sweet spots to reduce the impact of linearity. It'd be nice to assume what the CMM salespeople tell you, that it's accurate all over, but do a laser interferometry calibration of that CMM, and you may find out otherwise. Stability. Stability looks at the difference in ranges over time. That's how it's defined. I find it more efficient to evaluate stability by the use of a control chart. Repeatability is the amount of variation that we see if the same operator measures the same part with the same gauge. You measure the same thing over and over and over again, and you end up with slightly different results. That is repeatability error. Reproducibility, the fifth of these 5 definitions that are used to assess measurement systems, takes a look at the differences between operators. So we can think of repeatability error is within operator variation, and reproducibility error as between operator variation. Now, the purpose of inspection is to accept good parts and to reject bad parts, or to give us information that we can use for continual improvement. But from an inspection perspective of qualifying parts, we want to accept good parts and reject bad parts. If we have measurement error, and we always do, that measurement error contributes to the measured variation, and it works just like the Pythagorean theorem. The measured values, the values that we measure, they're the hypotenuse of this triangle. And the actual process variation is somewhat smaller than that. And so we typically look, based on the MSA 4th edition, at requirements, say, from 10% to below 10% is wonderful. That'd be our small measurement variation. 30% may be acceptable. Above 30%, not so much. And what happens is if we rotate the measured variation, if we put this on a hinge and we rotate this down, we get measured variation that's quite a bit larger than our process variation. But if we have small measurement variation, then the length of the hypotenuse is very similar to the length of the process variation. That's why we want small measurement variation. This is the size of the measurement variation. And if we're trying to inspect parts, to make a decision to accept or to reject, if we find a part that is in this central region, we're always going to accept that part. And if we have parts way out here, we're always going to reject those parts, assuming that we measure those. Where we might make bad decisions. The impact of this measurement uncertainty is we may, if we're near one of the specification limits, we have the potential to measure a part and say it's within tolerance, but it's really bad. And so we ship it to our customer and it doesn't work quite right, or it causes warranty concerns. Or we have the other concern where we reject good parts. We have parts that measure just outside of specification, and so we put them in the scrap bin, or we rework them, when in actuality it was a measurement error that made a good part look bad and cause us to reject. So last session I talked about statistical problem solving and Hans Bajaria's approach. It applies equally well to measurement processes. We identify and remove the causes of instability first. Then we look identifying and correcting the causes of too much variation second. And third, we deal with the bias or off-target conditions. So the fundamentals of MSA concepts. These are all of the things that we talk about in the full course. So we spend quite a bit of time here, but again, I'm limited on time, so I'm going to highlight in on some things that I think are real important, and then I'm going to end with a nice story of the tale of two inspectors. So you'll like it. Common use of MSA terms. What is a measurement? Oh, a gauge, a measurement system. This concept that they use the term a measurement system, because that's what we're talking about here is measurement systems analysis, really goes back to a standard on calibration systems, M-1, which it was published by ASQ. I don't know if it's still available, but I'm sure you can find it somewhere if you were so inclined. Interesting concept. A measurement ensemble. That's what you have with you think of the word ensemble with some musical group. You know, a quartet or a quintet or something, an ensemble that plays strings or some other instruments. Well, this includes all of the things that impact our measurements. They specifically say that the item being measured is outside of the scope of the measurement ensemble. So this does not include part-to-part variation. Or if we had a part that was out of round and changed diameter based on where we were measuring it because it was out of round, that wouldn't be included with this. This is the measurement ensemble, pure and true to itself, the way the instruments play with each other. Then we have the concept of a standard, the accepted basis for comparison. A known value, that I call it the true but unknown value, because it's only known within some limits of uncertainty. We need to know what those limits are. Those are the types of things that we should look for in a defined laboratory document of scope. Now, what are you capable of measuring, and what are the limits within which you can measure it and be able to trust your values? If we look at the basic equipment, we're interested in discrimination, readability, or resolution. How small of a unit can we measure? Well, sometimes we get a digital readout that goes to the 5th or 6th or 7th decimal place, and it does not represent the effective resolution, the sensitivity of that gauge for a particular application. And then we have a reference value and a true value, or at least what we consider a true value, the certified value for some given artifact. Now, if we look at location variation, the things that cause us variation in mean shift, the accuracy, the closeness to the true value, the bias, the systematic error, the stability, the linearity, those are all measures of central tendency of the measurement process, of location variation. The width variation are described in terms of its precision, its repeatability, reproducibility, or put them together for the Gage R&R, or the measurement system capability or performance. The capability looks at a short-term study. The performance looks at a long-term study, just as we did the difference between CPK and PPK in our last session on SPC. Uncertainty, the tolerance interval for measured values. Now, if you look at statistical intervals, we're pretty familiar as quality engineers with a confidence interval, but there's also a prediction interval and a tolerance interval, and each has their own operational definition. This is a tolerance interval, not a confidence interval. The measurement system has to be stable and consistent. If we look at the words standards and traceability, we expect to find an unbroken chain of comparisons traceable through all the way back to the national reference standards that are housed at the National Institutes of Standard and Technology. The purpose of inspection, again, differentiate between good parts and bad parts and act appropriately, because there's a cost if we get it wrong. The properties of measurement system that are important: adequate discrimination, sensitivity of the gauge. And we can consider that for product control or for process control. The measurement system must be in statistical control. The random effects model is essential to any of the statistics that we're doing in a measurement systems analysis study. If we don't have statistical control, the analysis done on those gauges are faulty. They're not trustworthy. We can't trust the results. In fact, Dr. Deming said if a measurement process is not in a state of statistical control, a measurement process does not exist. So the impact on variability is to avoid these two types of mistake: accepting bad parts, rejecting good parts. That's on the variability on product control. On process control, it's to take the right type of action when that action is appropriate. That's what a measurement system study should be telling us. When should we take what type of action? Here we have it, a tale of two technicians. It's based on the thoughts of Wheeler and Lyday evaluating the measurement process. So they get all the credit for this. It's just I borrowed heavily from them. So in this situation, we have two technicians, as you can tell by the title. Technician 1, he worked a day shift. Boy, people thought real highly of him. Instrument was always calibrated. Every hour he checked his gauge against the standard. If it didn't read 0, he reset the gauge to 0. And people saw this behavior and they say, wow, Technician 1, very careful, very conscientious, good guy. Now, Technician 2, he worked a night shift. He used the very same instrument. And every hour, he checked his gauge against the standard. But you know what? He attended the automotive division course on SPC, and he decided to record that reading on a control chart. Instead of making hourly adjustments to the gauge, he only adjusted the gauge when the value showed that it was out of statistical control. Otherwise, he just continued to use the gauge, no adjustment. Well, the two technicians were operating like this for several months. Finally, their supervisor became aware. She decided to study the results. She created two histograms. Variation from zero, variation from nominal. You can see that technician 1's histogram is more narrow. That there's more variation from the measurements of technician 1 than there is in the measurement process by technician 2. Well, how can this be? Technician 1, he was the guy on day shift. He was the conscientious guy. Those hourly adjustments made during the day shift made the histogram wider. The variation of those adjustments were called tampering with a stable process. And they were added to the natural variation of the measurements themselves, which represented the width of the second histogram by technician 2. Many of those adjustments were unnecessary, and every single one of them added to the variation in that wider histogram. Technician 2, on the other hand, the narrower histogram, he only adjusted the gauge when it was shown to be out of control. It needed adjustment. In fact, technician 2 almost never made an adjustment except at the beginning of his shift to accommodate or to take away the adjustments from the day shift. So based on this study and based on this story, a new calibration procedure was adopted across the company, and control charts were made a routine part of every single calibration scheme. How many of you calibrate your instruments based on a monthly schedule or a weekly schedule or a biannual or annual schedule, instead of making adjustments in response to lack of statistical control? Several of the companies and test methods showed immediate dramatic improvement and reduced cost associated with over-calibration. The use of a control chart to check consistency of a measurement process provides a scientific signal of when recalibration is necessary. Preparing for MSA studies is our next chapter. Two of my favorite quotes here. A problem well defined is half solved. I believe this to be true. That's from John Dewey, the educational philosopher in the early 1900s. That's the contributor of the Dewey Decimal System. And in life, I've found it to be true. If you define well a problem, you're halfway there. Or Albert Einstein. The formulation of a problem is far more often essential than its solution, which may merely be a matter of mathematical or experimental skills. What I've found in life is I can hire a mathematician, I can hire an engineer or a physicist with experimental skill, but I have a real challenge finding someone who can come up with the statement of the problem. Not solving the problem in the back of a textbook, but a real analytic problem that has financial consequences and allows us to manufacture more cost effectively. Here's two important questions. The first, are we measuring the right variable at the right location? If we're measuring something else, then regardless of the Gage R&R, we'll simply be spending money with no benefit. And the second question, which of the statistical properties are important to this given measurement process. These are the properties that are going to guide how we're going to do the measurement systems analysis study. Here are 6 steps in preparing for an MSA study. You know, I have one client who lives by the Plan, Do, Check, Act cycle, and you've all seen that as a circle rotating and arrows pointing the direction of travel, and it's broken into quadrants. Well, this company decided not to break it into quadrants. What they ended up doing is taking the first half of that circle as being the plan phase and taking the second half of the circle and breaking it into 3 equal parts for the do, check, and act phase. And I thought that had some merit. So we select a number of parts, appraisers, how many trials are we going to do? We use real operators. We make sure that people understand the purpose of the study. We have someone who understands the study observing the data collection, the data analysis. We randomize. We do all the things we need to do to make sure we do a good MSA study. And then we move on to the next chapter. Mathematics of the MSA study. There's a number of different techniques that are covered in this, and there are some that I'm not going to have time to talk about today. I won't have time to talk about the ANOVA approach to Gage R&R studies, nor will I have time to talk about the attributes Gage studies. But these are what I am going to talk about. The first is methods to assess stability. And we can obtain a sample and establish its reference value back to some traceable standard. You know, this assumed true value. And on a periodic basis, we can measure this master sample some number of times, 3 to 5 times it defined, and then plot that on the data on a control chart. Now, we could probably start that, if we were so inclined, on, say, taking a series of measurements all in one day, so that we have the basis of plotting some control limits, and then back it off to once a week, and then back it off to once a month, as we're told by the data. So if we wanted to assess bias with an independent sample, so what we had just finished talking about is stability. If we want to assess bias by an independent sample, then we're going to have to pull a sample of parts and measure those. A single appraiser measures a sample. So it's one part in this case, some predetermined number of times, and then plot the graphical results. This is actually an example from the MSA guideline, and I was blown away by this. Can you see, just by looking at the plot of the data, that the data is going to be something a little bit better than 6? If we were to pull the average, because we've got 6 values to the right, or increased values from 6, and only 5 on the left. So it's got to be a little bit greater than 6. Well, part of my career was to build gauges. And my natural inclination is, if it's not on target, I want to adjust that gauge. But if this is the amount of variation that we're seeing, that would be tampering with a stable process, exactly like appraiser 1 or inspector 1 was doing in the earlier example. What we ought to do is to compute the average and compute the standard deviation and calculate the t-statistic to assess bias. bias. And if the average value lies within the confidence bounds, then we make no adjustment or we're tampering with a stable process. Do you get that? That was a shocker to me. A cognitive leap, as my friend used to call it. Assessing bias, a control chart method. My preferred approach, take a look at the data. Take a look at the plot of the data. Assessing linearity, at least 5 different parts that reflect the operating range of the gauge. You know, the highest value, the lowest value, and 3 somewhere in between. Measure each part multiple times. Plot the data. We have 3 common methods for Gage R&R. The first and simplest is called the range method, and this is actually some software that we'll be using in the class. It's all Excel-based, and it follows the examples in the MSA guidelines, so that's where these numbers happen to come from. The number of parts is 5. The number of appraisers, 2. So that this study can be done pretty darn quickly. And we look at the differences, the range, and we calculate the average range, and we compare that to process variation from some previous study, and if by checking 10 pieces, we know that we're consuming 3/4 of our tolerance, we're not going to make the 10%, certainly. We're not going to make the 30%. It doesn't pay for us to have a gauge study done based on the average and range method, which typically has 3 operators and 10 parts that are being assessed. Here is a shot from the Excel spreadsheet that's used on the average and range method. We've got 10 parts now, 3 appraisers, 3 trials each. So we're taking 90 measurements instead of 10 measurements. There's a cost associated with every piece of data we deal with. The acceptable number of distinct categories, a minimum of 5. That was from an earlier slide on resolution. Some information. Enter the data. Now this is a results page, and what we see here on this particular page is that the number of ranges that fall outside of the control limit, this is the upper control limit on a range chart. This is that threshold value. One of those values lay above. The process is out of statistical control. There's some cause. It may be related to the operator. It may be related to the part. It may be related to the equipment. We don't know, but we know that something exists. We ought to identify it and get it out of our system. Learn from it. Evaluating the measurement process, we're going to take a look at the data from that R&R study in a more graphical presentation in this area. We analyze the results for stability by looking at the range chart. If things are out of control, then we have some appropriate action to take. Well, this is a series of plots, and I've narrowed them down for this presentation to, I think we left 6 in, so this is the first of 6. This looks at an averages chart, and it looks at the stacked average because the 3 averages, this is 3 parts by appraiser C, 3 parts by appraiser B, 3 parts by appraiser A. And this is the average of those 3 parts. This is the average of part number 2. So this represents 9 data points, 3 averages, 1 for each of the 3 appraisers, for part 3, for part 4, for part 5, and so on. That's one look. To look at it as a stacked average, can you tell that operator C has some bias compared to the other 2 operators? That all of the measured values are lower for operator C. I don't know how you pick that up from a Gage R&R if you don't plot the data. So what we're suggesting to our audience is to plot the data. So this is a stacked average check. Now the next one is an unstacked. So these are the averages from operator A, from operator B, from operator C, and you can't pick up the differences that you could in the stacked. So it's nice to look at the data through different lenses. Here are the range charts. Stacked, well, this is our part that was out of control. It's related to appraiser B. That gives us a clue. Here it is unstacked. We still see appraiser B, and it's, this is B1, B2, B3, B4. B4 what? B4, it's still the same point, showing out of control. Something unusual happened, and we ought to be able to find out why, if we look. Here we see a scatter plot of actual values, and you can see where that high range is coming. Here it is. It's the first sample, second sample, third sample, fourth sample. Here we're looking at an error chart where everything is compared to nominal. And so the nominal, this 0 value, comes from the 9 different measurements for part 1, the 9 different measurements for part 2, for part 3. So from the red to the blue for part 3, this is part 4. Green is appraiser B. This is where we saw the excessive variation. So there's a variety of ways to look at the data from a graphical perspective on Gage R&R results. So I bring you back to this 3-step process for problem solving because it works so well with measurement problem analysis. The first step, identify and remove the causes of instability. Then, and only then, the second step, identify and correct the causes of too much variation. And last, take care of your bias problems, your linearity problems, those things that cause off-target conditions. So to bring this to closure, here are the 3 goals of this course: to give us a common language so that we can talk intelligently together. We can have meaningful conversations about what type of MSA studies are appropriate and what we want to learn from them. We should be able to use the studies to determine where the measurement processes require improvement, and then to use that information to achieve robust, capable measurement processes. So, I'm done with my presentation. It's time for questions and answers.
Okay, thanks, Mark. What a great topic and great presentation. If you want to go ahead and enter your questions into the questions box on your right-hand control panel, I'll queue them up for Mark. Okay, first question, Mark. What is considered an acceptable bias?
There is a standard on, and again, a lot of my background is in GD&T. There is a standard. It's ASME Y14.43, and it applies dimensioning and tolerancing to gauges and fixture design. What they say is to attempt to achieve 10%. So don't consume more than, if you were to put a tolerance on a gauge, 10%. That would apply also to the amount of acceptable bias. Other authors will take different positions on that and say there's times when it's just not cost effective to try and achieve a 10% error, and so that gives you some baselines.
Great. Next question. What Gage R&R is better, ANOVA or the X-bar&R method, and why?
Okay. I have dear friends with differing opinions on this. I say do both, because once you've collected the data, the analysis is cheap. What you get out of the X-bar&R, or the averages and range approach, is you get a clear signal of a lack of statistical control when it exists. And I think that's of value if you're going to act on that knowledge. Now, what the ANOVA gives you is, what it does is it will partition the sources of the variation and tell you how much of the variation are coming from parts, how much of the variation are coming from appraisers, how much of the variation are coming from the interaction of those. And if you're in a problem-solving mode, that's an important piece of or pieces of information as well to help you get to the root of the cause of the problem. So once you've collected the data, why not run the data through an ANOVA approach? It's back to what Dr. Deming said about planning for actionable data. And I recommend both.
Okay, great. Can you please explain again your concept of operational definition?
Yeah, technically, it's not my concept. So I first was introduced to it in reading Out of the Crisis, and Dr. Deming, he dedicated an entire chapter to the subject. It was chapter 9. If you want to look it up and read it, it's good reading. But it's actually from one of his teachers. Dr. Walter Schuhart, in his 39 text, talked about the need for having operationally definite meaning. Now, Dr. Schuhart and Dr. Deming were both physicists. The literature in the mid-1930s, I'm starting to hear some feedback, and I'm not sure why, but I'll try and keep my train of thought. The literature in the 1930s, Dr. Schuhart identified that, say, for acceleration due to gravity, if I were to drop something, how fast is it going to fall? 32 feet per second, 9.8 meters per second. We know that. We treat that as a constant. But in the literature of his day, he found that different scientists, using different methods, came up with different results. Just like if you were to try and quantify the standard deviation of a measurement process with a Gage R&R study based on average and range, you'd likely get a different value than the standard deviation you'd pull up from an ANOVA study. So you use a different method, you get different results. That's the first point, which requires a well-defined test. What are we going to do? What are we going to measure? How are we going to measure it? Now, where we have some common conflicts, sometimes or frequently, you use, say, a CMM to get your measurement data to get you through your PPAP process, and that's going to give you a quantification of measurement error. And then you try to go to a functional gauge so that you can just see if parts are conforming or non-conforming once you've eliminated the sources of instability. But people have a difficult time frequently in getting those two studies to correlate. You use a different method, you get different results. The first part is using a common test. The second part involves the criteria for judgment, and that ought to come from an intelligent approach to engineering, a rationally based tolerance strategy. If we're doing an MSA study and we're making parts based on tolerances that came out of somebody's hip pocket, then we don't know whether the parts are going to work well together or not. It's rationally based tolerance strategies that allow us to know with a high level of confidence that these parts are going to assemble and that they're going to last for their planned useful life. And that ties in a relationship between dimensional behavior, and hence the measurement systems, and the reliability and reliability growth of a product. And there's some interesting studies on that as well. The third part is we just use the information. We use that test and this criteria for judgment in order to make decisions that we accept or reject.
Great. What was the name of the book you referenced by Wheeler? And then to add to that, do you have a list of recommended reading as a follow-up to the MSA?
I do. I can add those. I can send those to you, Walt, and have you put them up with this file.
Sure.
But the book in question is Evaluating the Measurement Process. I have the second edition, but the third edition is out right now, and I'm sure there's some improvements to it. So Wheeler and Lyday, Evaluating the Measurement Process. If you go up, I think it's SPC Press, either .com or .org, and you can find your way there.
Okay, great. Can you explain
SPC Press? You'll get there.
Okay, great. Can you explain the most significant differences between the AIAG MSA version 3 and our current version number 4?
Boy, I wish I could. When I went to the 4th edition, this is it's typical for an AIAG publication when they up a rev level from 3rd edition to 4th edition to list the changes that have occurred. The 4th edition does not do that. And I've been unable to find significant differences between them. But as I broke out in preparing this webinar, I started with the 3rd edition because that is very, very annotated. I write all over, I highlight, I use different color pens to remind me of what I used to know, and that's part of what I did. Well, as I opened that document, there was a page that was folded and stuck in it, and it says new errata for the MSA 3rd edition. So I'm sure that they corrected the calculation errors that were in there, but that was not a significant change between the two standards that I could find.
Great, Mark.
I would love to hear feedback on that. If someone in the audience knows of these, if you could shoot me an email, I would really appreciate, kind of a short list of what the significant changes are, because I don't see them.
Okay, Mark, if you want to flip to your last slide with your contact information, people can jot that down. In the meantime, what is a blind measurement in an MSA?
I think that's just like a blind study in the healthcare industry, where somebody's given a new drug and somebody else is given a placebo, and the individuals don't know whether they're getting the new drug or the placebo, and a double blind is where the doctor doesn't know which patient is getting the placebo or the actual treatment, the new drug. It would be, for example, when I talked about that one gauge block with those 4 steps, that is a blind study because the person making the measurement doesn't know what the measurement ought to be. One of the reasons for randomizing is that sometimes people remember what part number 7 was. If you randomize the order in which you're measuring the parts, you take away part of that. Yeah, I don't know that you take away all of that, but that's what a blind study does.
Yeah. What sort of MSA studies can be done using qualitative measurement systems?
There are attributes gauges that will tell you conforming or non-conforming. Okay, it's just if you were to take the concept of any feature of size has a maximum material condition size and a least material condition size. If it's a hole, then the maximum material condition size is going to be the smallest hole. If it's a shaft, it's going to be the largest shaft. It's going to be what makes the part weigh more. And the least material condition size is the exact opposite. A go, no-go gauge is an attributes type gauge, and that checks. A go gauge will always check for maximum material condition size. A no-go gauge will always check for least material condition size. Now, I am of the belief, and this is not in the literature, or at least I haven't found it in the literature, that the concept of pre-control can be applied to that tolerance zone by adding a second set of gauges. So if you have a profile of a surface tolerance on something, and you have a fixture that holds the part for measurement purposes, and say a leaf that's machined that pivots into place so that there's some amount of distance between where that is, and then you can sweep that with a feeler gauge that represents the maximum material condition or the go size and the no-go size. Well, what I'm suggesting is that you can have a second feeler gauge that breaks that into quarter increments that would define your green gauge in pre-control. And if you're interested in that, you've got my email address up here. I'd be happy to have some dialogue with you, but I think there's a whole lot of merit there in that type of a structure. Now, I also worked with a leather manufacturer who was trying to grade leather into the type of leather that would, say, go into a Cadillac versus the type of leather that would go into a less expensive, more economical vehicle. And so they had 5 different grades of leather, and the worst of those 5 were used for coats and things like that. They never made it into automobiles, but they had 2 grades that made it into the lower cost vehicles and 2 grades that made it into the higher cost vehicles. We attempted to do measurement systems analysis studies on selecting those grades. And I don't remember exactly how those turned out, but it was an interesting experience. So best I can do.
Okay, thanks, Mark. Well, we're running out of time. There's a couple questions left. I'll pass them on to Mark, and maybe, Mark, you can follow up with these individuals with an email. But I'd like to thank you for your time tonight. A couple announcements. Our next webinar is going to be February 8th. That's APQP, so it's just coming up in a very short time here. And then the second one out on February 29th, we're going to have Duran, the CEO and president of Duran Incorporated, is going to talk about the Duran Trilogy. I'll have the information and registration information up for that, hopefully by tomorrow. These presentation slides will be up tomorrow. Give me till tomorrow evening to get them up. I won't be able to get that done tonight. And the videos, I've had a little bit of a problem getting the videos updated because they're so large of a files. Been having a little technical difficulties, but I think I got that worked out, and hopefully by this weekend all the videos will be up there as well. So thanks for attending. Hope to see you on February 8th. Thank you. Have a good night.
Thank you so much. Bye now.